Okay, in this video I'm going to be talking about heme, so how heme is created from iron, and then how it's also broken down. And so heme is actually a tetrapyral molecule. It's a complex with iron in the middle, and so this kind of keeps iron from causing its damages. And so this heme molecule can be incorporated into different proteins, such as hemoglobin, myoglobin, and then various enzymes to catalyze enzymatic activity, such as cytochrome P450. So heme can be created in two different places. It's created in both erythroid progenitor cells in the bone marrow, and it's also created in the liver, so by hepatic cells. And so they're regulated by different mechanisms. When there's high iron, this stimulates heme production in erythroid progenitors. And then in the liver is actually regulated by its end product, heme. So when heme increases, it actually inhibits the production by the liver. And what you'll see is because of that, because it's regulated by its final end product, if there's any process that stops the production in heme, there's no regulation to stop the liver from producing heme. And so what you end up getting is porphyrias, which are basically porphyrias are a buildup of any of the metabolites that are created when you create heme. And so I got the steps kind of written down here. I wouldn't recommend memorizing them unless Dr. Houston decides to really ask some of these questions. But basically, ALA synthase, it is the rate-limiting step in the creation of the process that creates heme. And then there's 7 other enzymes that actually end up creating heme. So all these intermediators are actually highly toxic. So if there's a block in any of this pathway, what you end up getting is toxic effects. So porphyrias end up in 2 toxic effects. You'll see that there's the neurotoxic effects, so neurotoxicity, and you also see photosensitivity. So with neurotoxicity, what you'll see is neuropathic abdominal pain. You'll see peripheral nerve damage or peripheral neuropathy. And so that will show up in such things as numbness and muscle weakness. And then finally you can get CNS damage, which will result in fatigue and also psychosis. And people have actually been admitted to psych hospitals for neurotoxicity. With the photosensitivity, so the neurotoxicity, usually you'll see that in the first couple of molecules created, such as ALA and porphobilinogen, which is like PBG. And then these later ones, what you'll see is they'll usually be recognized by photosensitivity. So UV light actually reacts with these, and they fluoresce, and that causes damages and reactions. And so with this one, you'll see this in actually these 4, the last 4 are actually all sensitive to UV light. And even hydroxymethylbilane, what it can do is it's not sensitive to UV light, but when built up, it actually degrades to uroporphyrinogen 1, and it is also sensitive to UV light. So these 5 are all sensitive to UV light and present with photosensitivity. Okay, so the cause of porphyrias are enzyme deficiencies, but you'll usually see acute flare-ups, and these acute flare-ups are actually caused, like acute episodes where it's actually present, are caused by anything that stimulates ALA synthase. So ALA synthase is the rate-limiting step, so anything that upregulates it will cause it to increase more of the products, and wherever the step is limited, there'll be a buildup of that product, and that will present with the porphyrias. So things that upregulate ALA synthase are estrogen, like acute infections, so the stress from infections, alcohol, and drugs. And all these upregulate ALA synthase, and the result will be a porphyria. All these porphyrias are genetic, except for one that is acquired. This one is called porphyria gutnia tarda, and this is actually caused by some form of liver damage. So if you have like liver disease, hepatitis C, or alcohol cirrhosis. And what it does is that will affect the pathway, and basically you got a buildup of porphyrias, and that will show up in, and that's one that's actually caused. It's acquired. So how do you test for porphyrias? Basically, if you suspect a porphyria, you can do a urine test, and with urine, what you'll see is the first few ones are highly soluble, so you'll see ALA, and you'll see PVG in the urine. Okay? And then you can also do numerous other tests to test for the other ones. The rest of them, as you go down the chain, they become more insoluble, so they'll actually be present in the stool. Okay, now moving on to heme degradation. So heme is actually broken down into bilirubin. And so to do that, there is heme oxygenase, which breaks it down into biliverdin, and then biliverdin reductase, breaks biliverdin into bilirubin. And so this happens in the liver, and then bilirubin can then, so this is actually unconjugated, and so to be excreted by the bile duct, it has to become conjugated, and then once it's conjugated, it's excreted into the small intestine through the bile duct, and then it can leave through stool. So if there's anything that actually blocks the excretion of bilirubin by bile, you'll actually see a buildup of bilirubin in the blood, which is known as jaundice. So that's what actually, jaundice is the buildup of bilirubin. Okay, so if you see jaundice, so what actually causes jaundice? Jaundice can be caused by numerous mechanisms. Basically, if there's a high breakdown of, or high turnover of red blood cells, so this high turnover of red blood cells from, say, hemolytic anemia, or if there's like ineffective erythropoiesis, or if there's hematoma, so bleeding, there'll be a lot of red blood cells being broken down, and this can cause for a spike in the bilirubin levels. If you have a problem actually in the liver, if you have some kind of liver disease, so say you have Sorry, I forgot how this one goes. Yeah, if you have something just wrong with the liver, that's all it is, okay? So if you have something wrong with the liver, it can't conjugate it, and that'll also cause an increase in bilirubin. And then if you have some kind of block in the bile duct or some kind of liver damage, another kind of liver damage, that prevents bile from being created, then you'll see that's another way in which bilirubin can be increased. So if you see jaundice in somebody, you'll actually order a test for them, and the test will come back. There'll be two numbers that you presented with. You'll get total bilirubin, and you'll also get direct bilirubin. Okay, so direct bilirubin is actually conjugated bilirubin, which is the soluble form of bilirubin. Total bilirubin tests for both direct and indirect bilirubin, which is unconjugated bilirubin. And basically, depending on the levels that you see, you can determine what kind of cause this disease will be. So, when you see very high direct bilirubin, which is conjugated bilirubin, the bilirubin has already been processed. It's been conjugated, it's soluble, it's ready to be produced in the bile. So there's going to be some kind of backup either in the liver, so it could suggest a liver damage, some kind of liver disease, or it could be something like cholecythemia, or some other bile duct obstruction. That basically prevents bilirubin from being excreted into the body. And in this, you'll actually see an overflow in the system. It goes into the blood. It'll be turned up in the urine. And what you'll see in these kind of cases is actually there'll be tea-colored urine. And because the stool won't have the bile in it, it'll actually be very pale, almost a pale gray stool. When you see something with high indirect levels of bilirubin, this is basically when the bilirubin has been broken down, but it hasn't been able to be conjugated yet. So you'll see this with hemolytic anemias, also some liver diseases where it hasn't been able to break down the bilirubin yet. And so in this case, this bilirubin is unconjugated, so it's not soluble, and what it ends up being is it's sequestered in the albumin, causing jaundice. But this is actually not toxic. And a way to test for jaundice is you actually look at the person's skin. It will be yellow, but you'll also check. The best way to check is you actually check their eyes. Because say if their skin's too dark, you can't see the yellow in their skin. So if you check their eyes, the eyes will be yellow. And say if you're to eat an excess amount of carrots or something that has a lot of keratin in it, that won't show up in the eyes. So that's why you look at the eyes. So then there's a couple disorders that you see. There's Gilbert syndrome. So with Gilbert syndrome, what you see is the person is actually unable to conjugate bilirubin, so it builds up in the blood, and like I said, it goes into albumin. This is actually found in 5% of the population, and it's actually asymptomatic, which checks for the jaundice. A more serious disorder that you'll see is Crigler's Naegger's disease, and this shows up in neonates, and this is similar to Gilbert's disease, except in this case, the unconjugated bilirubin can actually cross into the brain. It crosses the blood-brain barrier, and there it can cause brain damage. So it's a lot more severe when infants get jaundice than adults, just because their blood-brain barrier is not fully developed yet, and in that case, you'll actually see toxic effects from the jaundice.